Welcome back to the deep dive. So you gave us quite a stack of sources this time, all getting into network efficiency, specifically IP addressing and, well, the big one, subnetting.
Yeah, subnetting is definitely foundational. And you're right, if you don't tackle it, especially as networks grow, you just end up with, well, chaos, a big digital mess.
Right. And that's really our mission for this deep dive, isn't it? We want to give you that shortcut, the way to understand how you take these big, potentially messy networks and divide them, make them organized, efficient.
Structured.
Exactly. So forget being just a tech for a second. Think of yourself as you listen like a city planner. That's the analogy we're running with.
I like that, city planner.
Yeah. We're not building one huge, sprawling, frankly, unsafe city. No, we're zoning it.
Yeah.
Creating distinct neighborhoods, residential, business, industrial zones, but for networks.
That zoning analogy is perfect because without it, in networking terms, you get broadcast storms, everyone shouting, security holes everywhere. You waste so many IP addresses. It's just inefficient.
Okay, let's unpack the zoning idea a bit more. I get the efficiency point, I think. But, if I only have, say, 200, maybe 250 devices, does all this math, this division really help? Isn't it just adding complexity? Why not just let them all swim in the same pool?
But that's thinking short term. Subnetting is the architecture that prevents that future sprawl, even with 250 devices. We divide that one larger network into smaller, actually manageable subnetworks, or subnets. And we do it for, well, 3 really critical reasons that honestly make the initial math totally worth it.
Okay, lay them out for us.
First, you seriously reduce congestion. By segmenting, you create smaller broadcast domains. Think of a broadcast like someone shouting in a massive hall versus shouting in a small room.
Okay.
In the big hall, everyone hears it, need it or not. In the small room, the subnet, only the local devices hear the shout. Less irrelevant traffic means things run smoother, faster for everyone.
Got it. So, the noise from the industrial zone doesn't spill over into the quiet residential area?
Precisely. Second, and this is huge, you get way improved security. If your finance department is on its own subnet and there's some kind of security issue there, it's contained. It's much, much harder for whatever's happening in finance to just jump over to, say, the HR subnet without very specific rules allowing it, rules we set up later.
That containment aspect makes a lot of sense, very practical. And the third benefit?
The third one is efficient IP use. This is especially true with larger address blocks. Subnetting stops you from, allocating a massive range of 254 addresses to a department that maybe only needs 10 computers.
Right. You're not wasting addresses.
You tailor the neighborhood size to the actual need.
Okay, that nails it down. Each subnet really is like its own mini city. It's got its own local rules for traffic, for security. Makes sense. But now we hit the part that often trips people up. There get the math. How do we actually draw these borders using numbers?
We do. And let's stick with the example you pulled from the sources, which is a really common starting point. A Class C network, 192.168.0.0.024.
Okay, 24. That slash notation tells us the starting point, right? It means the default subnet mask is 255.255.255.0, 3 cents of 255.
Exactly. And that mask tells us, by default, the first 24 bits are for the network, leaving the last 8 bits for hosts.
And those 8 host bits give us $254, which is 256 total addresses 0 through 255.
But, and this is crucial, only 254 are actually usable for devices like PCs or printers.
Right, because you always lose 2. The first one, .255, is the network ID, like the street name.
It identifies the network itself, can't assign it to a device. And the last one, .255, is the broadcast address, the megaphone for that specific network. Also unusable for a regular device.
So 254 usable addresses in one big block, but our scenario says we need 4 separate neighborhoods, HR, finance, IT, sales. We have to carve up that block.
And this is where the core mechanism comes in. We borrow bits.
Borrow bits. Explain that.
Okay, think of the 32 bits in the IP address. The subnet mask, that 24, draws a line. Bits to the left are network, bits to the right are host. We're going to move that line to the right. We literally take bits that were originally designated for identifying hosts, and we reassign them to identify networks instead. We steal them from the host side to use on the network side.
Okay. So we're making the network part longer and the host part shorter.
Exactly. That's the fundamental trade-off.
And this leads directly to what you called the doubling rule, which you flag this. This is where it gets really interesting.
It really is. It's governed by powers of 2, and it works both ways. Every single bit you borrow from the host side, it instantly doubles the number of subnets you can create.
Doubles them. Okay.
But at the exact same time, each bit you borrow halves the number of host addresses available within each of those new, smaller subnets.
Whoa, okay. So more networks, but fewer hosts in each one. That's a serious trade-off.
It absolutely is. You have to plan. If you get greedy and borrow tons of bits to make, say, 30 tiny subnets, you might find later that one department grows and suddenly needs more than the, 6 addresses you left for it.
So the city planner aspect is key here. You need to anticipate growth before you start drawing these lines, before you borrow those bits.
That's precisely it. Balancing the number of subnets you need now and might need later against the number of hosts each subnet needs. That's good network design.
Okay, makes sense. So before we actually do the math for our 4-subnet problem, let's explicitly state the tools. You mentioned 3 key formulas, kind of like cheat codes for this.
Yeah, they really simplify things. Memorizing these helps a lot. Tool number 1 helps you figure out how many bits to borrow. The number of subnets formula. It's just $2, whereas in the number of bits you decide to borrow, simple, borrow 1 bit, $21 equals 22 subnets. Borrow 2 bits, $22 for 4 subnets. Borrow 3, $23.80, and so on.
Okay, $2 for the number of networks. Got it. That's tool number 2.
Tool 2 calculates the consequence of borrowing. Hosts per subnet. This tells you how many usable addresses you'll have in each neighborhood you create. The formula is $2, $22. Here, H is the number of bits left over in the host portion after you've done your borrowing.
Okay, $2, but hang on. The -2, let's pause there. Why -2? You mentioned it before, but why is it always -2 for every single subnet?
Because it's like a fundamental network tax you have to pay for every single zoned area. No exceptions. Every subnet, big or small, needs 2 reserved addresses that devices cannot use. The first one lost is the network address. It's always the first address in that subnet's range,
Right.
like 0.0, 0.64, 0.128 in our upcoming example. Think of it as the official postal address for that entire neighborhood. It identifies the subnet.
The signpost. Okay.
And the second one, that's the broadcast address. It's always the very last address in the range, like 0.63, 0.1227, 0.191. That's the megaphone address, used to send a message to all devices in that one specific subnet simultaneously.
The megaphone. Right. So signpost and megaphone, network ID and broadcast, always reserved, always subtracted. Makes sense why it's -2.
Fail to account for that -2, and your host count planning will be wrong every time.
Crucial detail. Okay, and the third tool, you called it the block size or increment, the shortcut.
Ah, yes. This is the elegant part. Instead of fiddling with binary math to figure out where each subnet starts and ends, you use this. You just calculate $256 text subnet mask value. Specifically, you subtract the value of the last non-zero octet in the subnet mask. The number you get tells you the size of each subnet block. It's the increment.
The increment. Okay, so that tells you how wide each lot is on our city plan.
Exactly. It tells you the starting address of each consecutive subnet. Makes mapping them out super easy.
Fantastic. All right, toolkit acquired. $2 for subnets, $2.22 with the hosts, and $256 text mask value for the block size. Let's apply it. Our scenario.
Yeah.
Start with 192.168, vary towards 0284. We need exactly 4 subnets for our 4 departments. Step 1, how many bits to borrow?
Okay, we need 4 subnets. We use the first formula. 2 N of dollars must be greater than or equal to 4. If any 1, 21 Tyler. Not enough. If any and 2, 22 equals $4. Perfect.
So any is $2, we have to borrow 2 bits from the host portion.
Correct. 2 bits is it.
Step 2, well, it's our new prefix, our new subnet mask. We started with 24. We borrowed 2 bits.
So 24 network bits plus 2 borrowed bits, so 26 network bits. Our new prefix is 26.
And what does a 26 mask look like in the familiar dotted decimal format?
It's 205.255.255.192. Those first 2 bits in the last octet are now part of the network identifier. 128 plus 64 gives you 192.
Got it. 255.255.255.192. That .192 is the key number now, which brings us to step 3, the block size, using the shortcut form.
All right. 256 echoes to text the last non-zero octet value, so 256 echoes from 22.
Which equals 64.
And that number 64 is magic. That's our increment. It tells us that our subnets will start at addresses that are multiples of 64.
So it defines the boundaries cleanly.
Super cleanly.
Okay.
Network 1 starts at 0, Network 2 starts at 64, Network 3 at 128, Network 4 at 192. It maps it out perfectly.
Okay, let's actually list those out. Show the organization that the increment of 64 creates. Let's do it slowly so you listening can visualize these separate zones.
Sure. Subnet 1 is 192.168.0.026. The network ID is 0.0. The usable range for devices is 0.1 through 0.62.
And the broadcast address for that first subnet?
That'll be 0.63, the last address before the next block starts. So 64 addresses total, but only 62 usable, thanks to the NIGAS 2 rule. 26 2 addresses total, well, that's 64 2 is 62. We had 6 host bits left, 8 initial 2 borrowed each 6.
Okay, subnet 2 starts right after, at the block size increment. 192.168.0.6426. Network ID is 0.64.
Usable IPs for Subnet 2 are 0.65 through 0.126, and its broadcast address is megaphone is 0.127, network ID 0.128.
Usable range 0.129 through 0.190. Broadcast is 0.191. Still 62 usable hosts.
And the last one, Subnet 4, starts at 190.
Perfect. So look at what we did. We took that single 24 network with 254 usable IPs.
And we traded it for 4 distinct, organized 26 networks, each one capable of handling 62 hosts. Zoning complete.
Masterful city planning. Now let's connect it to the real world. Our company with HR, finance, IT, and sales. We assign each department one of these 26 subnets.
Makes sense. HR gets the first one, 192.168.0.026. Finance gets the second, 192.168.0068.6426. IT gets 0.12826. Sales gets 0.19226.
And in each of these neighborhoods, we need that exit ramp, right? The way out, the gateway.
Absolutely.
Yeah.
Typically, you use the first usable IP address in each subnet as the gateway address. The gateway would be 192.168.10.1.
Usually, yes. For finance, 0.6426, the gateway would be 0.65. For IT, 0.12826, it'd be 0.1229. And for sales, 0.19226, it'd be 0.193.
Reserving that first usable IP for the router.
Yep.
And here's where the rubber meets the road, the configuration. Let's say you're configuring the router interface for the HR subnet. Maybe it's interface Gigabit Ethernet 00. You'd assign it the IP address 192.168.10.1. But just as important, maybe more important, is setting the subnet mask.
Not the old 24 mask.
No. You have to use the new mask that reflects our zoning, 205.255.255.192.
Because without that correct 26 mask, the router won't know about our new neighborhood boundaries. It'll still think it's one big 24 city.
Exactly right. That mask is what tells the router how to interpret the addresses, how to enforce the separation.
And once that's configured, what's the immediate impact we'd see?
Tangible results. Let's say you have TC1 in HR, 192.168.10.1026, and PC2 also in HR, 192.168.0.2026. They can ping each other just fine.
Because they're in the same subnet, same neighborhood?
Correct. Local traffic works perfectly. But now try pinging from PC1 in HR, 0.1026, to PC3 over in Finance, maybe at 192.168.103.7026.
What happens?
Ping failure. Request timed out. By default, the traffic stops at the router.
Because the router sees 0.10 is in the 0.026 subnet and 0.70 is in the completely separate 0.6426 subnet. They're different zones.
Precisely. The router knows they're in different networks because of the 26 mask you configured. And unless you specifically tell the router how to forward traffic between those zones, which is routing, our next topic, it won't.
Wow. So that links straight back to the security benefit you mentioned earlier. We didn't just tidy up the traffic flow. We actually built walls between departments by default.
You absolutely did.
Yeah.
If we connect this to the bigger picture, this segmentation, this subnetting, is the essential foundation for things like access control lists or ACL's firewall rules on the router. Because HR and finance are now mathematically distinct broadcast domains, you can write very specific rules. You could say, allow HR to access the web, but block any attempt from finance to reach HR's file server. That kind of granular control only works because subnetting created the separation first.
That really brings the city planning analogy home. We drew the zones, and now we can enforce different rules, different security levels for each zone.
Subnetting enables smart, planned traffic control. Reduce noise, better security, efficient IP use. It all stems from this.
So what does this all mean? Okay, it means you, listening, now have the concepts and the math. You've got the toolkit, those 3 key formulas to take any large network block and carve it up. Segment it into smaller, efficient, manageable zones.
You do it by borrowing bits, understanding that trade-off between the number of networks and the size of each network.
We did phase 1 of city planning. We established the zones, we built our mini-cities.
We did, and we saw the immediate result. By default, they are isolated. HR cannot talk to finance. The pings fail between subnets.
Right. Which is great for security in some ways, but not very practical if departments actually need to collaborate, right? So the critical next step is turning some of those ping failures into successes, selectively.
We've mastered the zoning. Now comes the task of building the roads and highways between the zones.
Exactly. So the separation is done. Here's something for you to think about. We need the infrastructure for, mail delivery or public transport between our network zones. How do we do that?
We've separated the traffic successfully. What's the next layer? What's the technology that lets these carefully separated 26 networks talk to each other and talk to the outside world, but only in controlled ways?
That right there is the essence of routing.
Yeah.
And that's where we'll need to go next.